to start the recording for this week. Again, welcome everyone to this is week 11, but it's week 12 of Intro to Quantum Computing. This week, we're going to be going through another section of quantum mechanics without really going into like the quantum information or quantum computing part too much yet. I guess we're at 74 people right now. So I'll get us started and then hopefully more people will roll in. As usual, we will have our Canvas attendance quiz. Wait, why won't this let me annotate? Oh no, okay. Let me pause this for a second and try to figure out why I can't annotate. Okay, I could annotate earlier. No, okay, now I can annotate. Okay, sorry for the delay. Okay, great. Cool. Okay, so we can, we have the Canvas attendance quiz passcode as usual in the bottom right-hand corner of every slide. I will also I have the attendance quiz the attendance quiz number for Canvas also up. It's number 3, in case you guys ever forget. And this week we're asking about if you took the first semester of the course, whether you feel like the math was like too fast, too slow, if you felt like you needed all of it, or if maybe we could have done a little bit less math background and you still could have like followed along with, we haven't really done too much math this semester in lab, but I guess in your homeworks, you do have a bit more of that. So if you have any opinions that way. Why is this so difficult to use? I'm like really wrestling with Zoom. They changed how it lays out and I don't know why, I just can't do it sometimes. Oh, I figured out what I need to do. Okay, cool. Now I can't find where my window went. Well, hopefully this is fine. Hopefully this is recording correctly. I can never quite tell. So I will find out at the end of class, I guess, if it's not. Okay, cool. So, and I will start the pre-lab Zoom feedback as usual. I know that I was told that this week was a bit rough for some people, that it was a lot of material pretty quickly, and that some people felt overwhelmed with the amount of, I guess the amount of like conceptual stuff that was covered. Even though it wasn't super mathematical, it is like kind of a weird idea, like all this measurement stuff. I've hinted at it quite a few times over the course of labs. So hopefully you guys were less surprised that the measurements change things, or how these experiments kind of run down, because I've tried to like mention it. That's the thing, like it's always like if you hear things multiple times, it's just less stressful and confusing to hear about it. But also, is the speaker not working well? I'm seeing in the chat, so I'm like on my monitor here, which is why I'm looking over here. Okay, it sounds like you guys are doing all right. Okay, so we'll assume that things are fine until otherwise demonstrated. But yeah, I guess I'm seeing mostly like 3s through 5s as usual for the lecture this week. Mostly 4s, which I guess is a little lower, but it's not. It's similar to last week. So I think it's our quantum numbers are fairly consistent, because we don't expect you guys to have like substantial background in any of these topics. So it makes sense that most of you are saying that you understood it maybe, but you didn't already know it in its entirety. Okay, so this week we're going to be going through kind of the kind of original like measurement based quantum experiment, I guess, like, or not, I think it's not totally fair to call it measurement based, but kind of is, where you're measuring the state of the electron, and your entire experiment is just trying to measure the state of the electron, and its spin specifically, which is the Stern-Gerlach experiment. So that's kind of like the bulk of the lab, as far as like technical content goes. But then we do have a large section on like unanswered questions in quantum that I want to highlight and hopefully get some feedback from you guys about what you think on this topic. Okay, so I've gotten comments. The YouTube video from last week was marked as YouTube Kids. So we were told to mark it as like educational or child-friendly content, but I guess maybe it got marked as for kids only, so you can't have comments on it. I will take a note of that. And I will bring it up with the coding school this week. Yeah, I guess I don't think I have a questions, or yeah, we don't have a question slide. So I'll take questions now and write them on this already busy slide, because that's just how I roll. I've gotten a question from Drew about how you get such small slits for the double slit experiment. So the most common way to, or the way that you pattern most small things nowadays is through optical lithography, where you create a mask, maybe like, let's say it's our slits. Let's do, oh, that's not a slit. Oh no, why did I drop? That's really ugly. Okay, I'm not an artist. There's a slit, there's another slit. So you make a mask that looks like that. And then maybe you have another material actually underneath it. So let's say like this is our mask. Let's say this is, I don't know, aluminum. And then we shine light. Through the mask that we've made. So you will, I guess, note that like we can't make anything smaller than, like we're kind of honestly like making the same thing that like we already have, we have this issue where like if we have these slits, then we can also have interference from the light going through our mask. So I actually don't know if you wouldn't use optical lithography for making a double slit experiment. You can do electron beam lithography as well, but you don't use a mask for that. But generally, I'm just gonna go through general optical lithography, and I may be wrong that you would never use this for making a mask or for making a double slit experiment, but you shine the light through here and you have like some kind of material on top here. I shouldn't use a different color, but whatever. And this is resist. And then you will, the light will like weaken part of it, and you'll end up with like a shadow of where these things are. And then you can like etch through the material with like some kind of chemical to make the shape that you want. And this is how optical lithography works. You can do the same thing with electrons. So if you like, I'd have to think through like all the numbers to figure out, like you're limited by the wavelength of your light. So it's like what lambda over 2 is the smallest you can do because of the same interference, or like it's diffraction of the light. Like it limits your minimum feature size. But we can instead use an electron beam similar, like it's actually exactly the same thing, or this is still resist. I will like correct my resist. But you can also use the same kind of electron gun, like shoots. That shoots electrons at the resist, and you'll use a different type of resist that will be weakened by like getting hit by electrons. And then it will do the exact same thing where you'll end up with your two slits. Like you can kind of dynamically actually choose where you want it to go, which is pretty cool. So like all these like like this is the exact same thing as the SEMs we mentioned last week, which is a scanning electron microscope. It's the exact same thing. And this is how you normally do like very small feature sizes. I assume this would not be affected by the double slit experiment, like aspect in of itself. I'm not sure if you'd actually be able to use optical lithography, depending on what you want to interfere. Like if it was light, I think I may have built myself into a corner a bit. But I think it makes more sense to like think of the optical lithography where you have a clearly like defined pattern, where this, you can write it actually however you want. Like I can start making squiggles. Oh, I don't want to do that. I want to make an erased squiggle. I can start making squiggles and just like put like random dots as I want with the electron beam, which is pretty fun. Okay, I will stop rambling on how you write these things. Is light a quantum particle? Yes. Well, I mean, we call it a particle, we call it a photon. So we can treat it particle-like, but it is fundamentally massless as far as we know, but we're pretty confident in that. Like we're not totally confident that some other things are massless, but we're quite confident that photons are massless, and they like again they move at the speed of light. So like mass gets kind of like questionable at that speed. And so we know the packets of energy. So like the fundamental like quantization of light, you don't have like a quantized amount of mass or charge or anything with like a photon, but you do have an energy. So that is a fun fact. The Zoom code is blocked by my camera. Is it? Is it something blocked by my camera? I moved everything away from my screen.
It may just be my tablet, because I'm joining in from that for the first time. So it may just be that.
Okay, that's all good then. Yeah, if it's not a problem for most people, then I don't want to like block part of my screen because I had that issue last week, but thank you for updating. Okay. Okay, there's a lot of questions. I'm gonna try to move, well, we're gonna have like, we don't have too much material this week, so I'll just keep going. And questions are more important anyway and like answering questions is more important than covering the content, in my opinion. Because you guys should cover it in lecture and you can watch it later if you want. Is it possible to entangle a number of particles? Victor asks. Yes, you can entangle as many particles as you want. It's just every time you try to entangle two particles, you have some chance it will work and some chance it will not work. And you will like decohere. And so you need, that's actually a big thing with what they call quantum memories, where they use defects in diamonds that have very long coherence times to store your quantum state. And then you might have like a very short term, like you can transfer it to something that's easier to control and easier to like entangle with. So it could be a superconducting qubit, it could be some other type of spin state, and you perform the entanglement operation. And then like, which is just a 2 qubit, like it's just your Hadamard and then CNOT gate, which we've covered a few times, but we'll do that like entanglement operation many times this semester. But you can entangle as many particles as you can fit in your coherence time. If your gates like all work out, you could store your entangled state and then like perform like entangle with another thing. There are certain like well-known like 3 qubit entangled states. There's one called like the W state. I'm in eraser mode, which is a 3 qubit state. There are also noon states, which are like, I think like 4+. And there are cat states that I believe are 3 qubit. I always forget which state is which and how many particles are actually involved. So if I have any off, feel free to correct me. I've gotten a question from Mo about the Stern-Gerlach, and we will cover that when we cover Stern-Gerlach, because I'll answer your question very explicitly then. And you can have like full entanglement of like your 3-qubit state could be like equal entanglement of like, or like I forget the term is, maximally entangled. You can have a maximally entangled 3-qubit state. It's just, it will be different than the maximally entangled 2-qubit state. Gotten a question from Amy about the difference between an eigenstate and an eigenvector. They are the same. We use eigenstate a little bit loosey-goosey, where like sometimes we're referring to the eigenenergies and sometimes we're referring to the eigenvector that corresponds to those. But generally, like they are the same thing, depending on like what we're using to define it as. If we're saying like this, if we say this is an eigenstate, that is also an eigenvector. But sometimes we use this same notation to refer to the energy level itself, and then it gets confusing because then it technically gets corresponding to the eigenvalue, but it's all kind of semantic. Cool. Okay, I've gotten, you guys have some very good questions, but are a little bit outside the scope for now, but definitely ask them on Piazza or like chat amongst yourselves. It's always good to like learn things on your own, because that's actually the big topic of this week. So now we're going to move on to the real bit, where there's a lot of questions that we've gotten that are questions that we really don't know the answer to. So these are the why questions. Why do electrons seem to interfere with themselves, the double slit experiment? We know that they have this like wave vector that does like corresponds to your probability through the Born rule, but we don't actually know what this wave vector is. We don't really know what this wave function like truly means. And that's something that is still an open question that we've kind of just moved on from, because we can mathematically describe it. We just don't have like a really nice intuitive picture as to what it actually is. Like if we want to manipulate the wave vector, what are we doing? Because we don't really manipulate, well, we interfere two wave vectors, but that really only corresponds to like the relative amplitude and phase, which I guess like is kind of the whole thing, but we're not kind of customizing our wave vector for the most part in most settings. And one thing that's also, I think someone mentioned, well, we mentioned Hamiltonian, not Hilbert space, but something that I think is really important to note is that a lot of quantum theory originally dealt with like infinite dimensional systems. So you can have like a wave vector that like, I guess you could have like your 0, your 1, your 2, I don't know, like 1, ... like you could have like infinity of these. And that makes all the math like pretty complicated, and intrinsically like all systems we deal with do have infinite levels. It's just whether we're resonantly dealing with most of them. So our 2-level system has infinite levels, but we're only dealing with 2 of them because we've scooched the others farther away, so you don't have to think about them. But if you're dealing with like a photon in a harmonic oscillator, all the levels are equally spaced, and so you end up with the effects of this being infinitely many levels, really complicating things. So that's something that I think, because we're mostly talking about 2-level systems, I just want to make explicit that these wave vectors are infinite dimensional, like our Hilbert spaces are like generally like infinite dimensional, and that makes everything quite a bit more complicated. We also have another why question that you may have asked. Why can't we know for sure the results of some types of experiments? So this, you could also say deterministically. I don't know how to spell deterministically. So we can see like this is the same thing. And what this means is if we initialize our particle into a plus state, like let's say we start with our plus state, we do a measurement in the z basis, then we could say, yep, that's a plus state, but we can't do that. That's not something we can do. What we do instead is we put our plus state, we go to our measurement in our z basis, and then we get, I don't really want that. We get a 1 state 50% of the time and a 0 state 50% of the time. But we can't say for sure on any given measurement which one we'll get. And that is really annoying and really weird. And that's something we don't actually know, like why we can't, or like why we can't deterministically predict why this is. We know mathematically, like we have this wave function, it's probabilistic. We know we can describe it mathematically how it behaves and that it behaves probabilistically. We don't know why that is the case. So that's annoying. And then we have another, this is more of a like, we've got another question we've gotten a lot is why do electrons have spin? We don't know. We also don't really have like a super great picture of how spin works. We often kind of describe it as like a spinning top where we have like our magnetic moment and then we have like a spin around it. But that's not necessarily a physical picture. All we actually know is, again, like all these can kind of be like summarized as we can describe things mathematically. Sorry if my writing is worse than usual. I feel like it's just not looking great today. But we can't explain why they are that way or what the math really means. And this is kind of reflected in the fact that we do reduce our Hilbert space down to 2 levels. So we decided, oh, this is hard. I don't like it. Let's instead just have 2 levels, like our 0, 1 or our 1, 0. Now we're at 2 levels. That's a lot easier to work with. It's a lot easier to think about. And all this math does work in all settings, but it's not super intuitive. So if you're confused and if you're like, I don't know why this is the case, some of these questions don't have answers. And yeah, I've gotten a question from Michael if spin is just the periodic oscillation of the wave function. You do have a spin component to your wave function. I don't know how is, like, I mean, it all depends on like what frame of reference you're operating in. A lot of times when we are dealing with spin, we are dealing with it in a rotating frame. So it depends like how you want to describe this wave function. But yes, you do have a spin term in your wave function. And the way we know we need this spin is we know we need conservation of angular, and to make conservation of angular momentum work out, we were like, well, we clearly have more angular momentum than we thought we did. That's a spin. We solved it. What is it? I don't know, but it's angular momentum. It works out that way. So this kind of like, this is a less like big philosophical thing, I guess, in these other two questions. But it is like very much an unsolved problem is what this really means and what the best way to think about it is. Because we can do a lot just knowing how to describe this mathematically, but if you have like a better intuition for what this actually means, rather than just like, oh, these two terms commute, these two terms like interact with each other, like we have this selection rule, like if you have a better intuition behind it, you can create better experiments and better ways of controlling these aspects. So yeah, that's what we don't know. But what do we know? Well, we know, like I said, what the possible results we can get in an experiment. So that's our measurement. We have 50% chance getting spin up, 50% chance getting spin down. We know the and we can assign a number to those and get the probability of each of these. So that's when we showed the SEM, like the experiment where they shot a single electron at a time last week. And we're like, we can predict where each of these electrons will end up, like not on an individual level, but on a statistical level. If we shoot out like 1,000 electrons, we can recreate pretty much the same picture because we know like what the probability of each thing is. So it's on a single electron picture, we're not going to match it 1-to-1, but on like a mini electron picture, we will. And we also do know ways of manipulating the probability of getting the result we want. So through destructive interference of two different wave functions, or interfering an electron with itself. So the, I guess, self-interference question is if we have an electron in a superposition state with two different wave functions, then those two wave functions can interfere with themselves. So that's how we can get this this interference pattern through our double slit with just a single electron, is because we can have multiple waves assigned to a single particle. And this superposition is not the same as just having, I guess, like the sum of these two wave functions in of themselves. So that's kind of like, that's the really unique part about quantum mechanics, is really just that wave function, that superposition aspect. And we do know other things, but I guess the question now is, what do we do knowing that some things are unknown? Well, we can say, okay, I'm too uncomfortable, I can't move on. I'm unwilling to just accept this and like start using this quantum mechanics and do quantum computing with it. I need to know the answers. And so a potential approach is to go, okay, I know I need to know. So what do you do? Well, you can work on quantum theory and become a physicist. So Albert Einstein, Fabiola Giannotti, Nima Arkani Hamed, they're all theorists that work on kind of like fundamental questions in quantum physics. And so if you want like these fundamental questions to be answered, and you want to be the one to answer them, then this course is going to go like a bit more into like a little bit of fundamentals, but the majority of it is going to be in the latter two sections. So if you are uncomfortable with these questions maybe, but you're okay moving on, you're like, okay, I get that we don't know it, but we can describe it mathematically. We can still do useful things with it without really feeling like we understand what this means. Then you can become more of an applied physicist, or an engineer, and develop uses of quantum theory, such as quantum computing. And so I'd say like they say in some of the TAs, I definitely fall into this bucket. I do very applied physics, and my background is technically in electrical engineering, but I should have probably majored in physics in hindsight. This is examples of like famous like more applied physicists like Clarice Diallo and Zubir Sachdev. I always forget how you say his name. but yeah, they are much more applied physicists. They don't deal with these fundamental questions as much, or if they do, it's more on it's more because they built something cool that allows them to look at these more fundamental questions, but they're not like as fundamental, I guess. They can create these cool states that we think we can create, but maybe they're not asking why these states exist in the first place. And then there's a third kind of option where you're like, okay, I understand that we don't know the answer to a lot of these questions, but I just don't care. I don't care that we don't know the answer. I can describe it mathematically, and that's all I need. I'll just go and plug it into my computer, and then it'll work, and that's it. Like, I'm moving on. So that is where Peter Shor or Love Grover, there's also Grover's algorithm. We didn't note that, I guess, up top, but he's also like, he makes algorithms for quantum computers. So this would be like a quantum computer scientist. You do more, I guess, I feel like honestly, these people are more mathematicians than anything else. But depending on, like, I'd say like Peter Shor and Love Grover specifically are more mathematicians, but there are also people that I'd say like more kind of engineers and computer scientists that do like more targeted math. Well, these guys are, they're a little bit more mathy, I guess. So some of our TAs are more like computer science, like quantum computer scientists that try to work on algorithms that maybe work with noisy intermediate scale quantum computers, or are efficient for a certain application, give you a quantum speed up, but they're not trying to fundamentally prove that this is like the most efficient. This clearly gives a quantum advantage. And so there's a whole range amongst even this. So I guess the question for you guys is, of these three, I don't think I put a slide on it. I did not. But of these three, where do you feel like you fall? Are you a quantum computer scientist? Are you an applied physicist? Or would you want to be a fundamental physicist and kind of answer these very fundamental questions about quantum mechanics? I'm interested to hear what your opinions are on this. So I've from Shruti that she wants to do applied physics. Dhruv wants to do more quantum theory. Adam wants to be him. You know what? You can do that too. Milan, if you want to do them all, like you can always do a lot of things. And I think a lot of people do a bit of all this. Like I'd say I do some work. I mean, I don't do any work that's really algorithm development, but I definitely do some like hardcore engineering work. But I also am interested in looking in like providing, I guess, experimental evidence for more fundamental condensed matter problems. So there is a bit of all of this. I'm going to try to make sure that everyone is on mute. If I can. Okay, thank you. I just heard some feedback. Okay. And you guys can, of course, unmute yourselves if you want to talk, but I just don't want feedback when no one's talking. So, oh, wow, you guys are really, love all the answers. Sahil wants to be a physicist. Michael wants to be a theorist. Lee or Lai wants to do applied work. Kazi's interested in being a computer scientist. Polars wants to be a computer scientist. And Ojas and Dennis wants to do more hardware. That you can definitely do that as a experimental physicist, or you could become an engineer of any kind. There's a lot of options. But seeing like a good mix of all three. Thank you, Diana and Pierre, and Jason, Surya, and Tomas. Yeah, I'm seeing a lot. Christian said he wants to do aerospace engineering. Nice. That is also, of course, you don't have to be in any of these buckets and do whatever you're most interested in. But it's a useful field to know about, I guess. Yeah, I definitely like I think philosophically, I'm very much like, I'm very much like the shut up and calculate group, which would be like Peter Shore and Love Grover. But what I actually want to do is I do want to answer like a lot of these problems. It depends on what problem you're talking about, though. There's some very fundamental, like more philosophical almost problems, which is kind of what the first group is hinting at. But Fabiola Giannotti, like she doesn't do like, she does fundamental research, but into things that are more like we can like theoretically or experimentally like demonstrate this, but it's not like a philosophical argument. It's honestly kind of fallen out of favor to be interested in this more philosophical stuff in general. So our more recent examples in Einstein are honestly a little bit not 100% accurate. But yeah, so that's our kind of options. But they're all really interesting in their own ways. So now I'm already at 8:35. I'm going to be so late, but it'll all be recorded. I'll keep going for as long as I need to, and you guys can all leave, and I will talk at the screen and then put it on YouTube so you guys can watch it whenever you want, or not. I mean, you can also just like go through the slides. So we're now going to go back to kind of the measurement aspect of all of this, and where that's one of our like fundamental questions is, why can't we measure something deterministically? Well, if we want to know what we're doing in general, we do need to measure it, and we do need to be able to reliably capture what state we're in with measurement. So to do that, we have like our little measurement symbol. And with classical computing, we put in a 1, we get a 1 out. But if we're in quantum computing and we have a superposition state here, so this is our superposition, we don't necessarily know what we're going to get. I mean, we know that, I guess we want alpha squared, we read a 1, or wait, we use 0. Ugh. Just writing things backwards all day today. And beta squared, that we get a 1, but we don't know deterministically what we get here. And I guess what we want to do is try to figure out if there's a way we could do something different, so maybe we get a more accurate depiction of the state. So we're going to go back to the double slit experiment. So we know that we can send the electrons one by one through a double slit and get the interference pattern. And this again is because we do have like a superposition state where we have like the interference of the electron's wave function with itself. And so we can do this recreation of the interference pattern forming we showed last week. But now we want to go actually backwards and go back to the gumball gun or the marble gun. Do they go to the left slit or the right slit? Well, we can look at this and like say, like, I know I shot it towards the left slit. I know it went to the left slit. So you can just put your friend right next to the slits and be like, yep, that went through the left one. And oh, look, it hit 1. I guess if it goes to the left slit, it hits the 1 point on the screen. Great. So now, if you want to move this into electrons instead, and we want to know if the electrons go to the left slit or the right slit, we can't just put like our friend nearby because we can't see electrons with our naked eyes. And we also know if we had a bunch of light in the room, then that would interfere with everything. So we're going to try to be a little bit more clever, and we're going to make we're going to put some electron sensors here, and we're just going to treat these like they're like smoke detectors. If there's an electron nearby, it detects it and it starts beeping. And we can see like we have our left slit electron sensor and our right slit electron sensor. And this way we can know what slit it went through and where it ended up on the screen and how that like created this interference pattern. So we're going to try to back out what's actually happening with our wave function, what's actually happening with our electrons. We want better than this probabilistic result. So we did it. We can detect this, and that's amazing. But then what happens at the screen? Well, this is what happens. We can simulate this. What do you guys notice is happening with our electron pattern? Most it's particle-like. Yeah, it's looking pretty particle-like to me. And there's a couple key phrases I want, I guess. Polar, so there's no interference pattern with Athena. She said just these two bands. Yeah, we no longer have our like little oscillation. We just have kind of like this square here and here. And that's like not what we wanted. That's different than what we had before. I didn't want that. Kushaga has said that the act of measuring changes the result. Yeah, it does, and that's really annoying. Or Alon said it actually becomes deterministic. It's a good. I guess that we do know like where it is. We've already kind of measured it. So we've between the point of measuring and like us measuring again, we've collapsed our state. That's what they say. Like we don't know what this wave function collapse actually is, but we know that by the act of measuring it, we've like if you're thinking of it as the Bloch sphere, you can say like, okay, we're on the equator of the Bloch sphere. We projected it onto the z-axis, and now it just hangs out there. Like it's not moving anymore. It's not in any kind of superposition. We just know the state that it's in. Ben said if you measure it, then store it, but then delete it before observing the measurement, then the wave pattern returns. I know there's like there are some weird experiments that have been performed. I don't know, some of them are not like, some of them have gotten some fuss around them, but haven't been replicated well. There's like this very famous like silicon oil droplet experiment this group in France did, where they saw the same kind of like self-interference effect. But many other groups have tried to replicate it and they haven't been able to. So it's not treated the same. I will definitely like read this afterwards about that, but I don't know too much about that particular experiment. But yeah, so this is changed the outcome. So without electron sensors, we have our oscillations. With electron sensors, we just have these two bands. I'll take a note. This delayed choice. I feel like I've heard that phrase before, delayed choice quantum eraser, but I don't know too much about it. There are a lot of paradoxes. And yeah, Ilana's noted that you can't sense the electrons without interacting with them in some way. If you have a very classical kind of sensor, then you're functionally tying your quantum state to like a thermal bath, and then it's all like just getting washed out. But even if you have another quantum state to detect your quantum state, like you have a single photon interacting with your single electron, if they're interacting strongly together, that's the whole kind of quantum measurement system we use for superconducting quantum computers is what's called dispersive measurement, where they're very weakly coupled. And whenever you have two quantum states, they actually hybridize to create a new quantum state. So if we say we have like our 0, so this is our 0 p, this p stands for pH. I'll say pH for photon, and our 1 pH state. And then we have our 1 electron state, and our 0 electron state. And maybe they interact in some way, then they actually, like if this was here, and this was here, this was here, and this was here, they will maybe like come, or that should actually go down, shouldn't it? I have drawn, it doesn't matter too much. The whole point is just they hybridize. So now we have something that's kind of like in between the two, where this is like our 0, 0. This is our 1, 1. And so this is called hybridization, where they're changing the state a bit. And that's the case in any even single particle measurements. But if you are very weakly coupled, then it doesn't perturb the state enough to actually collapse the wave function. There is a limit to what this amount is that you can handle. And there are a lot of like videos on this that I think people have mentioned. Victor mentioned Dr. Quantum. I think we have that linked at the end of the slides if you guys want to watch it. but the whole point is that we have no way of measuring it without perturbing the state at all. But we do have like kind of quantum non-demolition measurement techniques that we can use that will perturb the state, but not enough to completely destroy it. So that is an option that we have. But that's all using, like, I guess, quantum electrodynamics techniques, which we might cover a bit. This stands for quantum electrodynamics. Oh, that didn't quite fit. That's pretty fun. Yeah, okay, I am so behind. Yeah, the whole point is the measurement changes the state. But if you go back to our gumball picture where we don't have this wave function thing happening, we just have particles that are at some discrete point in space, we actually have no difference with our gumball sensors or our no gumball sensors. And we could see like, oh, okay, we just put like 2 layers of like where we detect it. We have like maybe 2 detector levels, but they can just go through. There's no change in the outcome. You can have your friend look at it. That all works out. Even if we could look at electrons though, we'd still be destroying the state just because we need enough light to see it. If we could somehow detect electrons without needing any light of any kind, then we could maybe be quantum non-demolition sensors ourselves. If we were like far enough away, we weren't causing any like heat for the electrons, but overall, like you're always going to interact with your electrons somehow, and you're going to hurt their state. So that's the big difference between quantum mechanics and normal, like everyday things. We can measure a table, like the length of a table, and the length is not going to change. It's not like, oh, the table could have been 30 centimeters long or 28 centimeters long, and when we measured it, we just made it so that it was 30, and then it's going to be 30 at every point after that, rather than being like a bit of both. But in quantum mechanics, because you are interacting with the state in such a way you're actually measuring the fundamental state of it, it does actually change the state that you're in, which is a bit annoying. And there are I guess like you can interact with things in a way that's like it's an interaction that's not strong enough to destroy the state, and there is like a limit on how strong that interaction can be. Exactly why, like exactly how that we get to this limit, I'm actually not sure. I know like how you derive it, I guess, but I don't know how it corresponds to destroying your state. But yeah, are there any more questions on the contents? Oh, we're a bit behind time. But yeah, I'll try to move forward, and then because I've tried to answer questions as we've gone along, then I'll answer questions at the end. Okay, so now we're going to electron spin. We're so far behind on this lecture, where we do have fundamental properties for all these particles that we're looking at. So we have our mass for electron, our charge of electron, and then our spin for electron. And this is how we often describe it, as this like kind of like magnetic moment pointing in some direction. And then we have our spin precessing around that. So it's like a top turning. It is misleading to describe it this way, but this arrow does correspond to our magnetic moment. And we can detect that. How exactly this like spinning aspect happens relative to that is not necessarily as well defined. We know the direction of a magnetic moment. We don't necessarily know how the spin really like how we know. I guess we know the relationship between our spin and our magnetic moment by what's called our gyromagnetic ratio. I'm going off into space, but we do know the relationship between our spin and our magnetic moment, but the actual like pictorial representation of spin is is potentially misleading. So I want to make that clear, but we're just going to move on and measure spin now, because we just measure things and we don't think about these fundamental problems because they're bothersome and you can do a lot without thinking about it too hard. So since our spin or our magnetic moment, since our spin corresponds to a magnetic field, or it interacts with our magnetic field, we can use a magnet to measure it. I think this phrasing is potentially misleading as well, but the biggest idea is just that the spin and the magnetic field, or the magnetic I think the magnetic field is intrinsically tied. We normally know like the energy term, or like I'll say this is I'll include both. Our energy, or our Hamiltonian, is our B dot S. This is our dot product. This is our magnetic field. And this is our spin. And this is a term you'll see in a lot of things. So you can, and that's only a portion of our Hamiltonian, but that is a term that you get a lot. And so we use our magnetic field to measure what our spin is, and we can see it. This will shift our energy levels. We can apply magnetic fields and see like how these interact. This is the Zeeman effect specifically. That's neither here nor there. But we know that we will only be able to measure the spin along the direction of our magnetic field axis. We can't, if our electron is oriented in a way that's not preferentially oriented towards the positive or negative magnetic fields, then we won't be able to detect it. And I'll make that more explicit in just a second. So if we're going to measure along our z-axis, and we have our electron going in, then we can have our spin up, which would be, we put in our 0 state, we fly through, and we're like, let's go up here. So that's our up. Similarly, if we put in our, there's 0 yet again, we put in our spin 1, we fly through, and we go to spin down. We could also measure along the x-axis. So if we like reoriented this and we said that, and so like now this direction, I guess, is our x, which is the difference between the two magnets. And here, this was our z, just to write it a little closer. Then we don't normally call it like spin right or spin left. We have like our plus or minus states. But if we did do that for this this like kind of macroscopic example, or not, it's like partially macroscopic example, then if we were in our plus state, then we'd fly over to this like what we called spin right just here. And similarly for any kind of direction with this. So now when we do the actual Stern-Gerlach experiment, and we send our electron with 0 state through the Stern-Gerlach experiment, this pointing in the z-axis, does anyone know where this electron is going to go? Yes, thank you, Polar and Drew and Angel, and or is it Angel, or like you should let me know in private chat, so I will do it right in the future. And Sudhir and Alex and Athena, Snehil and Tomas, Fahim and Kazi and Amo. So you guys have kind of noted where we're going to be in just a second at this superposition idea. So if we're just in our 0 state, it will fly right through and go right to here. It'll be in state 1. Now if we, or in state up, if we instead are in the 1 state, does anyone know where we'll end up. Thank you, Polar, and Drew, and Athena, Moog, Amy, and Xavier, and Pierre, and Asol, Jeffrey. Yeah, you guys are totally right. We will go right down to state 3, and we'll always end up here if we're in state 1, because we're not in a superposition state. We are like 100% in this one state. The reason why it's not 50-50 is because I guess if you're not like, so this magnetic field is not like even everywhere, which is why it pushes things in one direction or another anyway. Like you can see that there's kind of like a little divot in this. And so there is, I guess, a higher field in the center, or there's like a higher field, like the closer you are together, the more field there's going to be. And so you have like a higher field in the middle versus over near these sides. And so things are just like, they're not totally uniform. I don't know if I explained that totally right, but that's why we can get these to move in the first place. But then further, we have a non-superposition state. So we're not, it's like we can pretend like we've already measured it once, and we've collapsed the state to be something that we know the value of. So like with that gumball experiment where we know it's going to end up, oh, is it just to make it perpendicular in the entire area for the curve? You might be right, because we want it to be like uniform, and we will have fringing values. Yeah, you might be right. We'll pretend like whatever I said was right, and I'll correct it either in the notes or in Piazza. Okay, but to get to the important bit, we now want to do a superposition state where we have some, oops, why did that zoom in? Where we have some percentage in our 0 state and some percentage in our 1 state. Now, does anyone know where these electrons would end up? And now, thank you guys who had some ideas earlier. They have it right. Thank you, Dhruv and Dennis and Kazi and Surya and Xavier, Sahil and Amo and Henry and Amy. Yeah, we're going to end up with some percentage going to both. So we're going to end up with like our 50-50 shot on both of these. And the reason for that is because we are in the superposition state. It's not like we're just somewhere along the axis. We actually have some percentage, or like there's some percentage of the wave function that is behaving like it is purely spin up, and there's some percentage of the wave function that is behaving like it's purely spin down. There's no percentage of the wave function that's behaving like it's along the axis. So that's where this kind of block sphere representation breaks down, and that's where this measurement along different bases kind of breaks down, I guess, a bit. We still do have like, because if you were just like actually along that axis, it wouldn't move at all, because it'd be, or like, I guess maybe it would cause it to start spinning. It's not going to be along the axis of the spin. It's not going to interact with the spin in the way that we want, because it's orthogonal to the spin. So like in that case, it would just go to 5, but we know it goes half to each rather than entirely to the middle. So when we do this measurement in the X basis, it's maybe not totally the same thing. But now we're going to do the measurement in the X basis with our electron state in 0. So like I said, there is like, we could take this like the if the value was just or if we were not treating the value like it is a superposition of 2 states in our measurement basis, which it is, like this you could also treat as like our 0.71 plus plus 0.71 minus. And I think that's the better way to think about it. And that should inform you where you expect this to end up putting us. And so thank you to Fuller and Dennis and Xavier. So yeah, we would expect that with this measurement, we'd then end up as some percentage going here and some percentage going here. And so that is different than if I guess it was just like along the axis and it didn't move at all and it just went to 5. So I guess that's the best way to think about it, as always kind of reformulating things into your measurement basis rather than trying to intuitively like back out what you think you're going to get without doing it. Like I think the intermediate step is quite important. So key takeaways. Oh, I'm not behind. Wow, okay. I lied to you all along, and I'll answer all of your questions just to apologize for rushing. I didn't really rush this section, but I didn't go through questions, which I should have. But the key takeaways is that measurement interacts with your state. It will change your state. You can't measure the same thing twice, I guess, because the first time you're measuring it, you're measuring the probability of the actual wave function. The second time, you're measuring your collapsed wave function, where it's 100% going to be the same result the second time. So that is, I guess, to draw that out, that was like, we have our plus state, we measure it, we get our 1 state with 50%, or 0 state with 50%. We measure it again, we get our 0 state with 100%. So that's different than like these values are different. We cannot reconstruct the wave function with our second measurement. The Stern-Gerlach experiment, which we covered, measures the spin of the quantum system. And when measured, we can only look at the direction along, or the spin along the direction of the magnetic field and opposite to the direction of the magnetic field. We don't look at it just as I guess the net like orthogonal projection to the magnetic field. And the result that we get will depend on the orientation of the Stern-Gerlach magnet. If we orient it along our spin axis or perpendicular to our spin axis, our measurement basis is different, and this does correspond to the measurement basis we would do in a quantum computing system, where we can measure in this X basis, but the way we do it is actually kind of artificial, where we rotate, like we take, I guess, a Hadamard to rotate up. It might be like a Hadamard then an X, depending on like which kind of phase you want between them. And then you perform your Z basis measurement because you've rotated up along the Bloch sphere. And so your net result is measuring in your X basis. But technically, like, you're always measuring your Z basis because your Z basis is your energy, and your energy isn't observable, and your random quantum state cannot actually be observed by itself. You always need to have something that you can actually measure. So Ilana's asked if Stern-Gerlach is used to measure in modern quantum computers. No, it is a, I guess, is Stern-Gerlach does get you the superposition, so it is non-demolition, I guess. But I don't actually know why well, it does You have to detect where your state is at the end. So the Stern-Gerlach is just trying to provide some way of selecting between the two spatially, but then you are still selecting spatially, and so it is collapsing at the point where you do that down selection. So yeah, that's how I would explain it. Gotten some questions from Adam and Polar and Drew about the wave function that we end up with. So yeah, the wave function that we're in is just kind of, it is the kind of phase, the important part mostly, I guess, is the phase of the quantum system, like your relative phase, just determines how your two particles or whatever are going to interact with each other. And so to get like a wave function, to get like the result of your wave function, like you do just plug it in to your Schrodinger equation, where this is your wave function. The actual meaning, like the actual like description of like what a wave function truly is a little bit not clear. That was kind of like the point earlier, is that we don't really know what it intrinsically means. But we do know that it corresponds to the probability of your particle being in a particular state if you're in a superposition. Yeah. Yeah, Athena has asked what it means to be maximally entangled. So a maximally entangled state, like a Bell state, is maximally entangled. We've got like your half 0, 0 plus half 1, 1, where like you are entirely in these two. These are entangled states. You can be entangled, like you can be less entangled, where you have like some percentage not entangled and some percentage entangled. So it's you're not required to be in a maximally entangled state all the time. Oh, and actually, while I'm here, before you guys leave, it is past 9, so you're of course free to go. But I will do our post Zoom poll just to see how this week went. Last week went quite well. This week, I think I rambled a little more, but hopefully it was still useful. Yeah, if I've gotten a question from Drew, if the wave function is like an actual function with a formula, I mean, like it's the results of the wave function is this normally like they're dependent on x and t, or x, or I guess this x can be like x, y, z in time, but you could also write your wave function in terms of momentum, or I guess you mostly just do position or momentum. Yeah, it is a function of I guess observable things like your position. But yeah, seems like today went also all right. And like most of you guys like got slightly better off over the course of the lab, so hopefully it was helpful. Yeah, I have a little bit of optional content that I just have to get through for the sake of the recording, so you guys can go if you wish. I hope you have a wonderful week if so, but I will just go through. I'd also like to point out the further reading that we do have available, that I think one of these might be the Dr. Quantum one that you guys can look into if you want to learn a little bit more on it. And then our optional content is on our 2-level systems. So I don't remember if someone asked about 3-level systems last week. 3-level systems are better, but they are hard to control. 2-level systems are easier to control because you do really have just 2 options. Like if you're not in one state, you're like, clearly I'm in the other one. Where if you have 3 systems and you measure one state, you could be in one of 2 other options. So it gives you a lot more complexity to deal with. And it also allows us to have everything be analogous to a classical bit if we operate with a 2-level system. So again, like we're just trying to reduce our Hilbert space from this infinite dimensional mess that's really hard to deal with mathematically to just 2 dimensions. And that makes it a lot easier to do things with. So the 2-level systems we deal with around us could be like a step ladder like this. You could say this is our 0 state and this is our 1 state, like whatever you want. You could say this is our 0 state, this is our 1 state. A transistor behaves the same way as these switches. So whenever there is transport between these 2, like if you have a bunch of electrons going between here, then that's on And so that's your one state. So there are a lot of two-level systems everywhere, but our quantum system is, I guess, unique because it is extremely well controlled, and it is exactly one coherent state that we can manipulate. So in the quantum world, some of our examples for a two-level system could be this double slit experiment, where our two possible levels are something that have spatially gone through here, something that has spatially gone through here. We can't really detect it or back that out, but that is a two-level system because there are two spatial modes that we're dealing with. Our electron spin is also a two-level system, our spin up and our spin down. All of the two-level systems are kind of based off of the spin up, spin down concept, because originally most things were done with cold atoms, where you just have like one valence electron hanging out that is in like an up state or a down state. So this is like kind of the traditional, like the most traditional. Picture. And everything kind of uses this spin phrasing, I guess, because it was originally all developed for electron spins. But we have a similar kind of circulating current model that you'd use for what's called a persistent current superconducting qubit, where you have your counterclockwise or clockwise circulating current. And the cool thing with these circulating currents is that they're, in superconductors, these can be persistent currents where they continue without any applied voltage or any energy being added. So that's like a unique superconducting part. So the difference between these classical and quantum two-level systems, which might be reviewed for you guys, is that you can have your combination of both, and this is where you get your quantum advantage. Sorry, my writing is so bad. Oh, I know why. It's because I stabbed myself by accident over the weekend. I was trying to open a box, but that's neither here nor there. So we get a combination of these two levels rather than just these one levels. And so you can say that this is similar to music, where you could have, this is one of Oxy's editions. I guess he's into classical music. I don't know anything about classical music, so I don't have a strong tie. These, if say only Shankar plays is a one state, Menuhin plays it's a 0 state. If they play together, we can have this superposition or this like interference between the two states as well. And so that's fundamentally different than this classical state, where if you tried to put it in like a superposition of 0 and 1, just put it kind of in between, it's really not a state. It's not meant to be. It's not stable there. But you can have this state just exist, and so that's unique. So I guess I've gotten a question from Tomas. Would be useful to use more levels to compute things faster. Long term, I don't think we would ever want to do that, just because the controllability is annoying. And we could probably make a larger quantum computer with like 200 two-level qubits, like qubits, and they call three-level qubits like qtrits, rather than having like a smaller number of qtrits. It'd be hard, like the fidelity and like the quality of your computation would probably be net better only using qubits. So that's really why people use it. But people do occasionally note the like qtrit aspects. Like, since I work on quantum simulation, this is something I pointed out, and I haven't influenced these slides by my own biases. But with quantum simulation, you're doing like a more analog version of any of these operations. So you're not just doing gates, you're actually simulating a Hamiltonian that does fundamentally have 3 levels, or like many more levels really, but 3 that you might reasonably see. So if you have like n qubits, you have your 2 to the n states. If you have n Q trits, you have 3 to the n states. And so if you're trying to make a quantum advantage argument for something analog, you like to use this number because it's bigger. And so you'll see that in papers. But it's for like digital quantum computing where you're really performing gates on these states, it's most realistic to just say it's a qubit. Although the fact that there are higher levels does play a role. Like when there's a C phase gate that actually uses the 2-state to perform this operation. So it is a very good question, and people are interested in using Q-trits, and there is a lot of research in it, but I think it is likely to remain research, but it is very interesting, and there are probably applications where it will become like preferred. Yeah, oh, that was actually the last slide. Okay, cool. I thought I had one more for some reason. Is a 3-level system ever used in classical computing? Kapsi asks. Trying to, like, I don't, like, you wouldn't call it a 3-level system in of itself. Like there are, I guess there's 3 port things that exist where like a transistor is technically 3 ports. So you have like your source, gate, and drain, and you apply your control on your gate, and that affects whether it'll go high or low. But it's always 2 levels. I'm sure someone's probably made a 3-level version, and there is a whole field of what they call analog computing, where they use continuum states that have like infinite values, or like say like you have like 10 options, or like realistically infinite options. And that is an active area of research, and it is very useful for specifically like machine learning problems where you have this exponential growth with your matrix size. And if you can parallelize it, that is an active area of research, and people are using all kinds of things like optics, like resistor networks, like all kinds of innovative things to do more analog computing like stuff. But I'm quite over time, but I think it was a good discussion. I can answer any further questions on Piazza, but I do need to go for tonight. But it was wonderful talking to all of you today. Yeah, I hope everyone has a nice week, and we'll be back next week, I think, with a little bit more quantum computing related material. Bye, everyone.